Hello and welcome. Today we're going to be continuing with Chapter 3, Motion in One Direction. When we're speaking of motion in one direction, we're going to be considering either motion in the X direction or motion in the Y direction. After this section, we'll be able to define both acceleration and velocity. But very importantly, we're going to distinguish between instantaneous and average acceleration and velocity. We're going to have insight into differentiation and know how that's a tool that we're going to be using in our work. We're also going to be deriving the equations of motion, finding out where they come from. Then we're going to be looking at deriving equations for objects in free fall. That's to say objects acting under the force of gravity. And then, of course, solving problems on the above concepts. We start then with the definition of displacement. In the previous chapter, we spoke of the scenario of a bug walking along the path shown by the dotted red line and moving from point A to point B. And we said that the displacement is an arrow which points from the starting position to the final position. If we look at the definition, the displacement of a particle is defined as its change in position over some time interval. This, vector delta x, written as a vector, that's the displacement. This is defined as the difference between the final position and the initial position, represented by these two vectors. It's important for us to recall the difference between a displacement and distance. So we said displacement is a vector shown by the red line pointing from the start to the end. And distance walked is this actual distance of this red line as walked by the bug. It's very important for us to be very precise and concise with our definitions, as the definitions, they form the starting points of solving problems. We look now then at the definition of average velocity. The average velocity of a particle is defined as the displacement vector divided by delta t, where delta t is the time interval during which the displacement occurred. If we look at the notation, we note that the velocity is written as a vector. It has this arrow above. And this subscript x means that we're referring to, velocity in the x direction. This subscript average, it refers to the fact that this is the definition for the average velocity to distinguish it from the instantaneous velocity. If we look at these points here, it says note that the velocity is a vector. That's something we've already spoken about. And also, the average velocity is the resultant displacement within a time period. No information about the actual path is taken into account. So it considers only a straight line between the start and the finish, which is this displacement vector. The use of language and definitions and terms in physics is very precise, and now we're going to be looking through an example that helps us to understand the difference between position and displacement and the difference between speed and velocity. So the scenario that we are looking at is that of a car, and the car is moving in the x direction, and the car is given different positions named A, B, C, D, E, all the way to F, and then at different times it appears at a different position. So if we look at the starting position at time t equals to 0, that would be when you start your stopwatch, the car would find itself at position x equals to 30 meters. So in the drawing, the car is over there at 30 meters. My little car here, I have it at a 30 meters starting position. Then when we reach point B, you can see some 10 seconds has elapsed, and the car is now at a displacement of 52 meters. Note these are positive values, positive 52 meters. So this means that during the first 10 seconds that the stopwatch was running, the car has moved to this position here at 52 meters. What happens next is the clock runs from 10 seconds to 20 seconds, and after 20 seconds have elapsed, the car finds itself back at position 30 8 meters displacement. So this means that it's moving in the backwards direction. Let's have a look. Where's their figures showing it there? After 30 seconds have elapsed, we now dealing with point D. We find that the car is at 0 displacement. So that means after 30 seconds have elapsed, the car is all the way back at the beginning. And carrying on like this, we see up to point F. After 50 seconds have elapsed, the car is at minus 53. So the car is now at this position here, minus 53. Remember, the negative sign means that we're on the left hand side of the x-axis, and the positive sign means we're on the y-axis. So given this table of events, this table of positions, of times and displacements, we see that the scenario that we're dealing with is a car starting at 30 meters and moving forward, and then heading in the negative direction, and then when the experiment ends, it stops there. So we can, perform a number of different calculations relating to this. We can also plot a graph of the position. So if we would like to plot a graph on the y-axis, we're going to plot the displacement of the car, and on the x-axis we're going to have the time running by. You see, at time equals to 0, at t equals to 0, we see the car is at 30 meters. We make a dot at 30 meters. That's position A. At position B, after, let's check what the elapsed time for position B is. For B, the elapsed time is 10 seconds, and after 10 seconds we see that the car is now at 52 meters. So this is how they managed to arrive at the second point B, and so forth. They plot point C, D, E and F. Remember, for the final point, let's check what the coordinates of F were. F was, after 50 seconds the car was at minus 53. X equals to minus 53. For this reason, in the graph, after 50 seconds, the point is negative. It's gone below the y-axis. It's now at minus 53 in the final position. Let's take a look at some calculations relating to this scenario. So in this example, we asked to find the displacement, the average velocity, and the average speed of the car between positions A and positions F. So remember, position A was the starting points at t equals to 0. It started at 30, and position F was once it had traveled all the way in the negative direction after heading in the positive direction. At position F, it found itself at minus 53 after 50 seconds. So the first thing we would like to know is the car's displacement. If we look at the displacement, it's given by the difference in the final position minus the difference in the initial position. And along with displacement, when we asked to calculate the velocity, that's given by the time that's elapsed. It's the displacement divided by the time. We just saw that in the definition. So calculating the car's displacement, then we remember, we only interested in the final position and the initial position. For us, the final position, this x at F, point F, this position was minus 53, where the car finds itself at the end. Then we have to subtract from that the initial position. Well, the car started over here. Its initial x coordinate was 30. So this is where this distance 30 comes from. We have minus 53 minus 30 gives minus 83 meters. The time that elapsed during the experiment was 50 seconds. So this gives us a displacement of negative 1.7 meters per second. The negative is significant because it means that the car ended up on the left of of its starting position. It ended up on the minus side relative to its starting position. So that's the meaning of the negative sign. Secondly, we need to calculate the speed associated with this journey. Remember when we spoke about the bug, we said for a distance, we would be interested in the actual red line that the bug walked along. So when we calculate speed, what we need to do is we need to take the distance traveled by the car and divide that by the time elapsed. So remember, in the car's path was starting here, then traveling forward to position 52. So once it moved forward, I'm interested in now finding the distance that it traveled. So when it headed forward, it's got to this point here. It would have traveled from 30 to 52, which is a distance of 22 meters. 22 meters in the first part of the journey. Secondly, it started moving in the negative direction. It would have, after some time, it would have come to the 0 position. So this distance here would have been an extra 52 meters that it traveled. This is 52 meters traveled backwards. So far in the journey, it's traveled 22 meters plus 52 meters. Then as it travels to the final position, it travels from 0 to minus 53. So this indicates that it travels an extra 53 meters. So the total distance that it would have traveled is then the 22 meters. That's this one, the 22 meters, plus the 52, plus the 53, and if we add these three together, then we get 127 meters. This is the distance it traveled. For speed, we take the distance, 127 meters, and we divide that by the time elapsed, the 50 seconds, and we find that to be 2.5 meters per second, which is the speed, the average speed of the car. We now take a look at the definition of instantaneous velocity, and it's defined as the rate of change at any position at any given instant. This at any given instant is important. It refers to at any given moment in time. So the instantaneous velocity, it's a vector. It's in the x direction. It's given as, again, the displacement divided by time. But in this case, we have this term, the limit, as delta t tends to 0 in front. And when we have this, concept of the denominator tending to 0, this indicates that we're dealing with a derivative. This is something you would have seen before in school in the definition of derivatives, and something else you'll cover in your maths course. So the limit as delta t tends to 0 of the displacement over the elapsed time. This is the derivative of the x with respect to time. Dx dt is the derivative of x with respect to time. In other words, the instantaneous velocity is the slope of the displacement time curve. For us to take a look and see where that comes from, we remember that when we were interested in defining the average velocity, we could have done that from the graph by considering the displacement over a period of time. And the average velocity would have been this delta x divided by delta t. But now, when we're interested in looking at the instantaneous velocity, what we really are interested in is at a given instant. So that is to say, at a given moment in time. So for instantaneous velocity, we don't want to be working over a very long period of time, delta t. We want this period of time to be an instant. We want it to be a very short period of time. Another way of, drawing that short period of time in the graph would be to draw a very little triangle. If we draw a very little triangle, a tiny baby triangle, then this displacement delta t at the top, it's very, very small. Delta t becomes very, very small, and we get a very small triangle. And then it turns out that the gradient the line that results from this consideration is precisely the gradient of the graph. So this is the gradient. By limiting delta t to 0, we have, as delta t approaches 0, we have a very small triangle that we're working with. And as a result of this triangle, it means that we're working with the gradient of the graph. And we know whenever we work with the gradient of the graph, we can find that by differentiating. So to find the instantaneous velocity, we decrease delta t to 0, or approximately to 0, until we're dealing with a point that uses a tangent to the line, as shown here. And then that gives us the instantaneous velocity. As you know, the magnitude of velocity refers to speed. There's a nice example for us to think about the difference between average and instantaneous velocity, and that has to do with traffic enforcement, speed fines, testing people's speeds. So sometimes you may have seen, if you're traveling in your car between two cities on a long distance trip, you'll come to some kind of structure across the road with cameras, and there will be a sign that will say average, speed trapping taking place, average speed enforcement in place. So how this kind of camera works is, you'll be driving, and then when your car passes under this boom, there's a camera that takes the photo of your car, and from your number plate it recognizes who you are. But this camera, it also records the time at which you've passed the boom. So this may be t0. Then perhaps you'll drive a very long distance, or a relatively long distance, maybe some 10 or 20 kilometers along the way, and then there'll be another boom, right? And at this other boom, it will take your picture again, recognize your car from the number plate, and it will check what time you passed under this boom. These two booms are far apart, in the order of several kilometers. Here I've written 20 kilometers. And then from this, it will calculate your average velocity, your average speed, because it will know the distance between the two booms. That's the length of the road you've traveled along. And it will also have recorded your time. It can calculate your average speed during that time. So this is a nice example of instantaneous, speed fines, instantaneous traffic speed enforcement. Another type of fine, perhaps you would have seen, you have a camera, and you'll be driving along the road, and if you're driving too fast, you drive past this camera, and the instant you pass this camera, it takes your photo and it records that you've been speeding. So one way such a camera may work, it may have two sort of lines in the road, or triggers, and it will measure, at that instant, what is your speed? How long does it take you to cross these two lines? At that instant, it measures your speed. Perhaps it does this with a physical sensor in the road, or perhaps with a laser. But the point is, it's measuring your speed at that instant as the elapsed time tends to 0. This delta t tends to 0 is another way of saying that the time it takes for this measurement to take place, it's in the order of milliseconds. It's a very short time, which is different to the average enforcement, where that happens over minutes or tens of minutes as you travel the 20 kilometers. We move on now to take a look at the definition of acceleration, and as with velocity, we're going to have average acceleration as well as instantaneous acceleration. Well, acceleration of a particle is defined as acceleration. It's a vector, once again, in the x direction. The average, it's defined as the change in the particle's velocity divided by time. This change in velocity, this is the final velocity minus the initial velocity over the elapsed time. So as I pointed out, the vector delta v, that represents the particle's velocity, and delta t is the time over which the velocity changed. So note that acceleration is the rate of change of velocity. Remember that velocity is a vector with both magnitude and direction. So velocity is a vector. Vectors have magnitude and direction. So if we're speaking about velocity changing, it can change either in its magnitude, or it can change in its direction, or both the magnitude and direction can change. Next, we take a look at the definition of instantaneous acceleration. And this is the rate of change of velocity at any given instant. So we have the instantaneous acceleration. Again, it's a vector. This is given by the rate of change of velocity, and the fact that it's at any given instant is represented by this limit as delta t tends to 0. In the limit as the time tends to 0. And of course, this notation represents a derivative. So the instantaneous acceleration is the derivative of the velocity with respect to time. If you look at this, we can rewrite the acceleration. Acceleration is the change in velocity with respect to time, as we see above here. But you can rewrite v. You can rewrite v as dx dt, right? The velocity is the change in position with time. This is something we saw before. So you have rewritten v in terms of dx dt. If you now take the derivative of this bracket, then you see what we're doing is we're taking what we call the second derivative. We're taking two derivatives. So we can rewrite this as the second derivative of x with respect to time. Here we have some consequences that follow. If the change in velocity with time is constant, then acceleration is constant. Remember, acceleration is defined as the change in velocity with time. An example of this is free fall, where we have the Earth's gravitational constant being 9.8 meters per second squared in the negative j hat direction. A second note is if the velocity is constant, then the change in velocity is 0. It's easy to understand that if something's constant, then it's not changing, so the change is 0. If the velocity isn't changing, then it means that the acceleration is 0. An example of this is constant linear motion. As I said before, we need to be very precise with our use of the terms and the definitions in physics. Let's briefly chat about now what it means for a particle to be accelerating. Well, acceleration implies that there's a change in velocity, and velocity is a vector, and as such it has a component, the magnitude, which is the speed, and the direction. So if something is accelerating, it means that the velocity is changing, which means that either the magnitude of the velocity is changing, either the speed is changing, or the direction of the velocity is changing, or both of these two are changing at the same time. If we speak about the speed of something changing, this would mean that the car perhaps starts at rest, and then as time goes by it sort of accelerates and moves faster and faster. So it starts off moving slowly and then it goes faster and faster. Under this case, its speed would be changing. if we refer to its direction changing, then it might be, traveling at the same speed the whole time, but it might be turning and changing directions and traveling in different direction the whole time. This would also be a case whereby the velocity is changing because the direction is changing, and as such the car would be accelerating. The third case for acceleration is both the magnitude and the speed could be changing. So this is to say that the car could be going like this. It's changing direction, and the whole time it's changing speed. Let's do a problem to test our understanding of the concepts of average velocity and instantaneous acceleration. So in this problem, they say the position of an object is given as a function of time by, the position is a function of time, x is a function of time, is given by this expression. We can see it depends on time. Question 1 is to find the average velocity between ti equals to 1 second and tf equals to 2 seconds. The reason for this subscript I refers to initial, so the initial time of 1 second and the final time of 2 seconds. The way to do this problem is to always, start with the definitions. That's an excellent place to start. For average velocity, we concern ourselves with the initial displacement and the final displacement. And the definition of average velocity is the difference between the, it's the final displacement minus the initial displacement. So for us, the final displacement is going to be the position of x at tf equals to 2 seconds. So the final displacement, x is a function of tf, is going to take place when t is 2 seconds. So what we do is we substitute in wherever we see a t, we write a 2. So this then becomes 2 times 2 to the power of 4 plus 3 times 2 to the power of 3 plus 2 allows us to calculate the final position as 58 meters, which we will use for this term over here. We also need to know what is its displacement or its position at t equals to 1 second. So to do that, we substitute 1 in for t, and we find that when t is 1 second, the position x is equal to 7 meters. Going back to the definition of average velocity, it's the difference between the final and the initial. So it's the 58 minus the 7 divided by the time that's elapsed. Well, it's between 2 seconds and 1 second, so that means 2 minus 1 second has elapsed, and we find then an average velocity of 51 meters per second. In the second part of the problem, we asked to calculate the instantaneous acceleration at t equals to 2 seconds. So the clues in this question are instantaneous. Whenever we think of instantaneous, we think of the limit as delta t tends to 0, and we realize that for instantaneous we're going to be differentiating. For acceleration, we need to remember that acceleration is the derivative of velocity, and acceleration is the second derivative of position. So this means that we're going to be needing to work with our expression for position, and we're going to be needing to differentiate it twice to give the acceleration. The first time we differentiate it, it gives us the velocity. So remember the rules for differentiating. To differentiate this first term, we take the 4, we multiply it by the 2, which gives 8, and we decrease the exponent of t by 1, which gives 8t to the 3. When we differentiate 3t to the power of 3, we get 9t squared. This is a constant, so it falls away during the differentiation. So the first time gives us the velocity as a function of time, but in the question we actually asked for the instantaneous acceleration. So we need to differentiate the velocity term once again. to give us the acceleration. So this gives 24t squared plus 18t. That's the general expression for the acceleration as a function of time. But in the question we asked what is instantaneous acceleration at t equals to 2 seconds. So this means that we need to go the one step further, and we need to substitute t equals to 2 into the expression. Wherever we see a t, we need to write a 2, and then we can calculate the final answer to be 132 meters per second squared. So we now take a look at deriving the equations of motion. Equations of motion are something you've no doubt used before, but it's going to be important to see where they come from, and specifically where they come from in terms of the definitions that we've already defined. So the goal then is to predict the motion. We must derive equations for different quantities, for the position x, for the velocity, the acceleration, at any given function of time. So this is the goal, to have expressions for each of x, v, and a at any given time. These are the 4 equations that we're actually going to derive. So to start the derivation, then we're considering motion only in one direction. So this is to say, for example, only in the x direction. We're going to be dealing with constant acceleration, so the acceleration isn't going to be changing with time, and we're going to represent this acceleration in the x direction. Simply, it will be equal to the average, and we're just going to call that a. So the symbol we're going to use for the constant acceleration is a. From the different definitions we've already seen, we've seen that the definition of acceleration is the change in velocity with time. So it's Vf minus V over time. Another way to express an average, and this is a very natural way to express an average, is to add, the final and the initial quantities together and divide by 2. So this is the second fundamental equation we have. The third, from definition, the definition of the average velocity, remember that's the difference in the position, the final minus the initial, divided by the difference in time. Now, simply for us to simplify the notation and to make it a little bit more comfortable, we're going to define some of the symbols in different ways. So we're going to call the final velocity, we call this v. We're going to call the initial velocity vi. We're going to rewrite that as u. Then we're simply going to say that the initial time is 0. So that's fine. It's like saying when we're doing our experiment, we're starting our stopwatch at time equals to 0. So this is a choice to set ti equal to 0. And then we're going to call tf, we're going to call that t. So you can see tf minus ti is going to be t minus 0, which is just going to be t at the bottom. That's why we're making that choice. And then I said the acceleration a is constant. So these choices here are really just to simplify and make the notation a little bit simpler. Next, what we're going to do is we're going to work with these equations, and we're going to make a number of substitutions and rearrangements to arrive at our 4 equations of motion. So equation 1, which was the definition of acceleration, we can simply call Vf v, we can call Vi u, and at the bottom we will have t. And then if we equation 1 then gives us acceleration is v minus u over t. If we rearrange that to make v the subject of the formula, we then have v is equal to u plus at, which is the first equation. This equation 9 is also going to be useful. This is just obtained by rearranging this expression, making t the subject of the formula. To find the second equation, we start with the definition v is the average of v plus u, so it's half of v plus u. And we also note that 3, by making use of this notation, 3, we can rewrite 3 in terms of this equation here. Velocity is equal to distance over time, or equivalently, distance is velocity times time. To find our second equation, we substitute equation 5 into equation 6. So here, instead of this v over here, I've substituted in half of v plus u. So we substitute 5 into 6. This gives us the next equation. S is equal to half v plus u times t. To find the next equation, the position as a function of time, what we do is we substitute 4 into 7. So this is 4. You can see 4 is the expression for v as a function of time. Into 7, here's a v. So instead of this v, we write u plus at. U plus at, there we've written it, plus u. Then we simplify, and we get the expression s is equal to half ut. S is equal to ut plus half at squared. That's our third expression. To find out our final expression, we substitute equation 9 into equation 7. So we substitute in equation 9 into equation 7. You can see this is 9 is an expression for t. So instead of this t over here in equation 7, what we're going to write is v minus u over a. We make that substitution, and now we have s is equal to half this product here. In simplifying this further, we notice that here we have v plus u, and it's multiplied by v minus u. So we note immediately that this is the difference of squares. We have v plus u, v minus u. So when we multiply these two together, it's going to give v squared minus u squared. The half still remains at the bottom, the a still remains in the denominator. So rearranging this and making v squared the subject of the formula in these subsequent two steps, we arrive at the expression v squared is equal to u squared plus 2as, which then gives us our fourth equation of motion. I'd like you to work through these steps yourself, and indeed practice them and become comfortable with knowing which substitutions to make and being able to arrive at the final equations. We're going to be using the equations of motion to solve problems, and these are the steps we're going to use to solve these problems. First, we're going to make a sketch of the situation, listing all knowns and unknowns. Then we're going to make sure that all quantities given are in SI units, in the same units, SI units. And then we're going to apply the equations of motion to find the unknown quantities. Really key to this process is going to be the care that we need to take with the directions and unit vectors. So when it comes to unit vectors, we covered that previously. We said a unit vector is a vector that points in a direction, either along the x-axis or the y-axis or the z-axis. So taking care with the directions of the unit vectors, we have the Cartesian axes, the x and the y-axis. As I've written it, this is the positive side of the x-axis. If we're looking for the number plus 100, it's going to be on the right-hand side of the x-axis. If we're looking for a number minus 1,000, it's going to be on the left-hand side. Similarly, for the y-axis, the positive numbers appear above and the negative numbers appear below. When it comes to the unit vectors, the unit vector for a vector pointing towards the positive x direction, we're going to use the unit vector positive r hat. Similarly, if a vector points in the negative direction, we're going to use the quantity negative r hat for the negative x direction. Our unit vectors for the y direction, you may have guessed it, if it's vectors pointing upwards, we're going to use positive j hat. If the vector is pointing negative, it's going to be negative j hat. So in terms of the directions of the vectors, we're always going to need to apply these sign conventions for the units vectors. Let's take a look then at an example. A car traveling at a constant speed of 45 meters per second passes a trooper on a motorcycle hidden behind a billboard. 1 second after the speeding car passes the billboard, a trooper sets out from the billboard to try catch the car, accelerating at a constant rate of 3 meters per second. How long does it take the trooper to overtake the car? Okay, right, so the wording of this problem, it's a little bit American language, but they're referring to a trooper, which we would call a traffic cop, on a motorcycle hidden behind a billboard, hidden behind a sign, right? Another word for billboard is a sign. So they're saying our car is going to be the red car. It passes someone on a motorcycle. We're going to use this black car to represent the motorcycle. This car is driving, and then after some time, this car chases him, and then they're asking how long does it take for the trooper to overtake the car? How long does it take for this black car to catch up with the red car? So that's basically the information that we've been given. The steps that we need to do is we need to make a sketch of the situation. So here I've done the sketch. I have an X and a Y axis. I have a sign, and here I have a motorcycle, and this is the car that's ridden past this motorcycle. We need to make sure that all the information is in SI units. So this is in meters per second squared. Great, that's SI units. Then we need to write down all the relevant information. For the trooper, the traffic cop, we're given that, well, let's start with the car. For the car, we're given that a car is traveling with a constant speed of 45 meters per second. So U is going to be 45 meters per second. The direction is going to be in the I hat direction, right? Because it's traveling in the positive X direction. We're told that it's traveling with constant speed, so that means that the final speed is going to be 0, also in the positive I hat direction. And because the speed is constant, it also means that our acceleration is going to be 0. We told, that for the traffic cop, he departs 1 second after the car has passed after the car's passed the sign. So this means that the speeding car is going to be traveling for 1 second longer than the traffic cop by the time the traffic cop catches up with him. So this is why I set the time for the car to t plus 1, and you'll note the time for the traffic cop, that's been set to t. We told that the trooper, the traffic cop, he sets out accelerating at a constant rate of 3 meters per second. This is this acceleration. He's also accelerating towards the right in the positive I hat direction. So I've made this positive I hat direction. He's starting from rest, so his initial speed is 0. U is 0 for the traffic cop. The question that we asked is, after how long does the traffic cop overtake the car, right? So for us to realize that when the cop catches the car, it means that the two vehicles have traveled the same distance. This is a key fact that we need to realize to solve this problem. When the cop catches the car, it means that they've traveled the same distance. Yeah, but both of them have traveled this distance shown. So what we're going to do is we're going to say the distance traveled by the cop is equal to the distance traveled by the car. The appropriate expressions for us to use is going to be the initial ut plus half at squared for the cop and ut plus half at squared for the car. The reason I've chosen to use that is because I know u for the cop and I know a for the cop. Let's just confirm that I know that. I know u for the cop and I know a for the cop. I also know u and a for the car. So here I've used ut plus half at squared. So the good thing about knowing u and a is that t is the only unknown. T is the only unknown on this side, t is the only unknown on this side. Substituting the values in, we see that this first term cancels out and we have this expression here. You'll note that what we have is a polynomial to t squared. We can rearrange this to come with an expression of t squared minus 30t minus 30 is equal to 0. Remember, we're trying to find the value of t, the time for which their two distances are the same. So this means that we just need to solve for t in this equation now. You can try to factorize it yourself and you'll realize that it's not possible to do this by simple factorization. So what we need to make use of is nature of the roots, where we use this expression minus b plus minus the square root of b squared minus 4ac over 2a. If we look at our expression, then the different terms that we have, a refers to the number in front of the t squared. So for us, a is going to be 1, b is going to be minus 30, and c is also going to be minus 30. So we substitute in for the values of a, b, and c, and then we get 30 plus minus the square root of 102 over 2. When we simplify this further, we come out with two different answers. And you're going to notice that when you calculate this answer, it's going to be negative, right? But in our solutions, we can't have a negative time. So it means that this solution is going to be incorrect. We can't accept a negative time as a solution because it has no physical interpretation. And then the solution rounded off to 0 decimal points is 31 seconds or 30.95 seconds. Right now we look at an example, and the purpose of this example is to make sure can you assign the signs correctly to the different quantities in terms of the unit vectors and the direction. So the problem says a car is traveling at a velocity of 10 meters per second to the left and is slowing down at a rate of 2 meters per second squared. The car comes to a rest after 25 meters, and we've been asked to write down the values as you would use in the equations of motion. So this is the situation. The car is traveling with a velocity of 10 meters per second to the left. So this means that when it starts off, it has initial velocity pointing to the left, right, in that direction. And it says that the car is slowing down. So if the car were speeding up, then the acceleration would be pointing in the same direction as the initial velocity. But because the car is slowing down in our example, it means the acceleration must be in the opposite direction to the initial velocity. So for us, the acceleration is going to be a vector pointing in the opposite directions. And the question asks, write down the values as we would use them in the equations of motion. So when we're working with the equations of motion, we're always interested in the same quantities. We're interested in V, U, A, T, and S. So, okay, we're not given the final velocity. We're not given information about V, but we certainly are given information about U. They say it's traveling at a velocity of 10 meters per second to the left. So this means that U is equal to 10 meters per second, and the direction to the left is in the negative I hat direction, in the negative x hat direction. So it's in the negative I hat direction. This direction is important. So the value that we would use for U in our equations of motion would then be minus 10 meters per second. Of course, this refers to the x direction. Minus 10 meters per second. For the acceleration, we've seen that the acceleration must be in the opposite direction to the initial velocity because it's slowing down. So we see that the acceleration is pointing in the positive x direction, which is in the positive I hat direction. So our acceleration is going to be 2 meters per second squared in the positive I hat direction. So the value that we would use in the equation then would be positive 2 meters per second squared, right? We're not given any information about the time, so we can't fill that in. But we are told that after the car comes to rest after 25 meters, so after it's traveled 25 meters to the left, it comes to rest. We need to take note that that the distance will be 25 meters, but it will be in the minus I hat direction. It's on the negative side of the axis. So the value that we would use in the equation then would be minus 25 meters for the final displacement, the final S value. Up until now, we've been talking about cars and objects moving in the x direction, but it's also important for us to look at motion in the y direction. So in terms of this, we're concerned with free-falling objects. So objects released from some height fall to the earth due to the force of gravity. This is something that's intuitive. We're aware of that. This is governed by Newton's universal law of gravity. This can be written mathematically by the force of gravity is given as the product of the mass of the object multiplied by big G, a constant, multiplied by the mass of the earth divided by the radius of the earth squared. And each of these terms circled in this bubble here are constants. You know, the mass of the earth doesn't change, the radius of the earth doesn't change, this big G is also a constant. So each of these are constants, and we can look up their values. You can look up the mass of the earth, the radius of the earth, and you can calculate that these terms in this bubble, their value is 9.8 meters per second squared. So this means that when we write the vector version of the force on objects falling towards Earth, it's given by the force's mass times this Earth's gravitational acceleration, g, and this is given by 9.8 meters per second. The direction is in the minus j hat direction. Whenever we're going to be using g, we're going to have it operating in the minus j hat direction. This is because gravity pulls an object down, right? So the direction of g is always going to be in the minus j hat direction, always acting downwards. Some further points relating to free fall. Free fall refers to objects subject only to the force of gravity. So if we're speaking of objects only subject to the force of gravity, it's free fall. Free fall can be straight up or straight down motion in one direction, and it's the y direction. So if we speak of an object traveling in the y direction only under the force of gravity, we're speaking about free fall. The four equations of motion thus still apply. The only difference is now that they don't apply in the x direction, but because we're working in the y direction, they apply in the y direction. And of course, this AY is going to be 9.8 meters per second in the minus j hat direction. I've already spoken about the importance of the Cartesian axis in terms of the directions, with right being plus I hat, up being plus j hat, down being minus j hat, and left being minus I hat. And now what we're going to do is we're going to look at an example of a person standing on the top of a building, and he's basically throwing a ball upwards, and that ball is reaching the top and then heading downwards. In terms of this axis, one important thing is we need to, when considering these types of problems, we need to make sure that we position the axis at the right place. So we're always going to position the axis such that the origin of the motion, where the motion starts, is where we place the axis. So in this example, we're going to speak about the person throwing the ball. The motion is starting, the throwing is starting where his hand is, so we put the axis at as shown. As I said, the y-axis is positive going upwards, and the x and the y-axis is negative going downwards. We're considering the motion of the ball negative going downwards. So what's interesting for us to do to look at this example and to look at the signs of the relative quantities, and to use this as sort of like a thought experiment and understand the quantities, understand the different signs. So they say a person is throwing a ball upwards it's thrown upwards at position A. At time TA it's thrown upwards, then it's going upwards, it's reaching the top. At the top it's obviously going to stop. This refers to position B, and then it's falling down past the person again at position C and falling down to position D. So let's have a look at the different quantities that apply to the different cases. At position A, that's when the experiment starts. So TA is going to be 0. YA, the initial y-axis position, is going to be 0. It's starting at the origin. We've put the origin where the motion begins. The initial velocity is 20 meters per second. It's in the plus j hat direction. It's plus in the positive y direction. This is why this value is positive. Gravity is acting on the stone. Gravity, we said, always acts downwards. Gravity always acts downwards. So for this case, acceleration is minus 9.8 meters per second squared. It's downwards. In fact, at each of the positions, at B, we can take a look and see that the acceleration is still downwards. It's still minus 9.8. It's acting downwards. C, minus 9.8 meters per second squared. D, minus 9.8 meters per second squared. This is because if you have an object and it's in the air, it's falling, gravity's always acting downwards, always pulling it down. So our gravity is always minus 9.8 meters per second squared. Let's have a look at the other quantities and see if they make sense. So as we said, at time equal to 0, the y position is 0. He's throwing it upwards at 20 meters per second. When the ball reaches the top of the trajectory, we know that it would have stopped there. It stops right at the top, right before it starts falling down. First moves up, then stops at the top, and then falls down. So for this reason, Vy is 0. It stopped at the top. The distance it went is 20.4 meters. We can't know that just by looking at this figure. That would be something we need to calculate. We've already spoken about the acceleration always being downwards. Then it stopped at B, then it starts falling downwards. The acceleration is minus 9.8 meters per second. When it gets to this point here, then the velocity now is in the negative direction. See the sign? Vy is minus 20 meters per second. This is because the ball is moving downwards. It's moving downwards. Again, the acceleration is always downwards. After some time has elapsed, it's now at point D. It's actually lower than where it started, right? So for this reason, its position, its y position, is now minus 22.5. It's below the y-axis. It's below the origin of the axis. The velocity is now going to be minus 29 meters per second. It's still moving downwards, and its acceleration is minus 9 meters per second. So here we have a good example of values being assigned to free fall motion in the y direction, and I want you to take careful note of the signs of the different quantities in terms of plus j hat and minus j hat. We now take a look at a concrete example. So we have an attacker at the base of a castle wall, which is 3.65 meters high. He throws a rock straight up with a speed of 7.4 meters per second from a height of 1.5 meters above the ground. Will the rock reach the top of the wall? The first thing we've been asked is, will the rock reach the top of the wall? So the first steps we need to do is to look at the problem quickly and see if everything's in SI units. We have meters, meters per second, meters. Fine, that looks good. Secondly, let's make a rough sketch of the situation. So they say that an attacker is at the base of a castle. He's at the bottom of a castle wall. They say that the wall is 3.65 meters high. And they say that he's throwing a rock up towards the top of the wall from a height of 1.55 meters. This is because as he stands with his hand extended, the rock is starting at 1.55 meters above the ground, and we asked, will the rock reach the top of the wall? So the way we need to tackle this problem is to draw our axes, and we draw our axes where the motion starts. So it starts at his hands, and we in the question are told that he's throwing the rock upwards with an initial speed of 7.4 meters per second squared. So for this reason we set u equals to 7.4 meters per second, sorry, not meters per second squared, meters per second, in the plus j hat direction, because it's going upwards. Gravity is always acting downwards in the minus j hat direction. And for part A, we've been asked, will this rock reach the top of the wall? Of course, the four equations of motion we have available are shown here, all in the y direction, of course. So at the highest point, the stone will have a velocity of 0. So that's, when the stone reaches the top of its trajectory, it stops before it falls down again. So at the very top, its velocity will be 0. So this means that we can make use of this expression here, and we'll know v squared will be 0. We're given the initial velocity. We know acceleration is minus 9.8 meters per second. So we can substitute these values in, and then we can calculate the distance s as 2.79 meters. So this is the distance from this point here until where the rock stops. It's 2.79 meters. If we want to know the total heights that the rock traveled from the ground, we have to add the 1.55 meters to that quantity to find the total height, and then compare if the total height that the rock reached, if it's greater than the 3.65 or less. So performing that calculation, we add the 1.55 to the 2.79, and we see the quantities 4.34 meters. So the rock goes 4.34 meters, which of course is higher than the 3.65 meters. So that's the solution to part A of the question. So for part A, we asked, will the rock reach the top of the wall? So the answer to that would be yes. For part B, we asked, if so, what is its speed at the top? So we need to calculate the speed of the rock at the top of the wall. So for part B, we say, okay, so for it to reach the top of the wall, it must travel 3.655 minus 1.55 meters. The reason you need to subtract the 1.55 meters is because it just needs to travel this little distance here, right? It's already starting at 1.55. So it in fact needs to travel a distance of 2.1 meters upwards. This is why this is plus j hat. So the value we're going to use is plus 2.1 in the equation. The appropriate equation for us to use then is this equation shown here. The reason for that is we know the initial speed of the stone. This is the plus 7.4 meters per second upwards, and we know the acceleration downwards. We've just calculated the distance here, so we can then solve for v, and the solution that we found is that the velocity at the top of the wall is positive 3.68 meters per second squared. Here we have a square root sign. We've chosen to use the positive answer because we know that when the rock reaches the top of the wall, it's still traveling upwards. We take a look at part C of the problem, which speaks about a slightly different scenario. They say find the change in speed of a rock thrown straight down from the top of the wall at an initial speed of 7.4 meters per second and moving between the same 2 points. So in this case described, they're saying, for example, there's a person on top of the wall now. He's throwing a rock downwards at 7.4 meters per second, and we asked to calculate the change in velocity between this point here and the same 2 points. The second point refers to this point 1.55 meters above the ground. So gravity will be pulling the rock downwards, causing its speed to increase in the minus j hat direction. And what will the speed of the rock be once it reaches this point here? So we solve the problem in much the same way. We start by putting our axis where the motion begins, and we list the knowns, and of course we need to take careful care in making sure that we assign the correct signs. So the rock is being thrown downwards at 7.4 meters per second. So for u, the initial velocity here will be minus 7.4 meters per second squared, where the minus indicates that the rock is being thrown downwards in the minus j hat direction. The acceleration is going to be minus 9.8 meters per second, again minus representing downwards. The height at which the stone will move between the 2 points, it will move downwards a distance of 2.1 meters. So once it reaches here, it will have gone downwards a distance of minus 2.1 meters. Of course, I use s is equal to minus, representing that it's in the minus j hat direction. For us to calculate the change in velocity between the 2 points, we should first calculate the final velocity here, and we can do that using this expression. V squared is equal to u squared plus 2as. Since we know u, we know a, and we know s, you can substitute the values in, solve for v, and the change in the velocity is going to be given by the final velocity, which we found here, and the initial velocity, which we are given over here. If you complete this calculation yourself, then you can go on to find that the solution is as shown here. We see the final velocity is 9.79 meters per second in the downward direction, so it's minus, and the change in speed is going to be 2.39 meters per second. Right, this concludes the work on chapter 3, where we've looked at motion exclusively in one direction at a time. And we've actually done that separately for both motion in the x direction and motion of an object under free fall in the y direction.